The topic of today's class is what's called gradient descent. Gradient descent is like the workhorse optimization algorithm of modern machine learning. Okay, so that's today's topic is gradient descent. So gradient descent basically is, so let me just take it back to the very first lectures that we had. So we talked initially about curve fitting, right? Which is kind of one form of what you call linear regression, okay? So previously, we talked about, curve fitting. And kind of what we came down to when we talked about that was that we wanted to find a set of optimal weights, which in that case were coefficients on polynomials, that were the minimizers of some cost function like this, right? This is like saying I had a matrix A, I had my vector B, and I had my vector W, and I wanted to find the best W that satisfied this least squares equation, right? Now this is what's called a problem that is linear in the parameters of W, right? So this is linear in the parameters, and hence that means that we had what was called a closed form solution, which we were able to write down, right? We were able to say that I could take this pseudo-inverse and solve exactly for the right W in one step, right? So this is when life is good. When we have a linear system, we can always solve this problem directly, okay? However, many problems in machine learning and more generally in the real world are not linear, which means that I can't simply jump right to the solution. Instead, I need to do some sort of an iterative optimization method to find the answer, okay? And so the good side is that those nonlinear models are often a lot more what you call expressive, meaning that they can do more than a linear model, right? So for example, we know that a linear model can divide the world into two pieces kind of above and below a line. A nonlinear model might be able to have like kind of a squirrely decision boundary that's maybe not even a continuous boundary, right? So there are lots of things we can do with nonlinear models that are great, which is why we care about using them, but that means that they are harder to optimize, okay? So let's just say, many machine learning algorithms or many machine learning problems are nonlinear in the parameters that we need to solve. Right? So these are more what I would call expressive models, but also harder to optimize what we're looking for, okay? So our more general problem may look something like this. I have the minimum over all my possible parameters W of some cost function, right? So we still have this thing that we would call the, cost function. And, we still might try to pose it something like, I want to minimize. So I might say, for example, that this function of W could, for example, be the sum of a bunch of square differences between something like this. So basically here, this is like my observation. This is like my model, and this is also like an observation. So it's like this is the observed input, this is the observed output, and what I'm trying to do is I'm trying to fit the model so that my function of the input parameters is as close as possible to the output parameters. But now this function here may not be a linear function, right? That's the difference between last time and this time, okay? So we're going to find a way to try to minimize this function in a iterative way, okay? Now, again, optimization is, again, a whole course in itself, right? So I know at RPI, for example, we have a course called Numerical Optimization, which I think is a great course to take, right? Because you'll not only learn about what I'm talking about today, but also there are all sorts of other extensions, which I will kind of touch on at the very end of today's class, right? But the one I want to talk about today is what's called gradient descent, okay? So, here's the setup, right? Like I said, we want to minimize some function over some set of parameters where this function maybe takes like an m-dimensional set of parameters and produces a number, okay? And so we say that W star is a, global minimizer, or more generally just minimizer, if the function at that point is less than or equal to the function at any other point. So a good example of that is something like this, right? I have a function like this. This function has a global minimizer here. And this global minimizer would be unique, right? There's no other place that has the same value. I could also have a situation where I have kind of like, flat areas of the cost function that are all global minimizers but not unique, right? So for example, if I had something like this as my cost function, then any of these points would also be a global minimum, right? But they're not unique. So this would be like saying I have a non-unique minimizer. Now, what happens in practice is that we have what's called a local minimum, okay? So the terminology there is that this is a local minimizer if this function is locally smaller than everyone else for all W, that satisfy something like this. That's like saying you're like a local guy but not a global guy, right? So for example, a function like this, right? This function here is a local minimizer. And so is this point, and so is this point, and so is this point. There's only one global minimizer, and that's this guy down here. So this kind of landscape is really where we're operating in the real world almost all the time, right? So some sort of complicated cost function that may have many minima, and we're just trying to find the best one that we can, okay? Yes, okay. So let's talk about how we might find one of these local minimizers, okay? So first of all, let me go back and say, like, how can we, this would be the great situation to be in, right? Our cost function looks like a big bowl, and we're just trying to find the bottom of the bowl, right? In theory, you can imagine if you just let a marble slide down the rim of this bowl, it would find the global minimizer, right? That's in a way exactly what gradient descent does, right? In a similar way, if you imagine this as some sort of like funky three-dimensional surface, if I let a marble go at any given point, well, it's going to fall into one of these kind of local minima, but it may not be the global one, right? So we want to be in this situation as much as we can. Now, we're not always going to be there, but there are some special functions that do look like this. And of course, we're not going to do it in 2D. We're going to do it in high dimensional space, right? So, so one class of functions is particularly nice for optimization, and that class is called the set of convex functions. So first I'll give you the math, and then I'll tell you what this means, right? So mathematically, a function is convex if it satisfies this property. Basically, it says that if I choose any 2 points, W1 and W2, that this property is true. So this is true for any W1 and W2 and any value of alpha between 0 and 1. Again, maybe not super obvious what this means when you just read it as an equation. Kind of more conceptually what this means is that if I connect 2 points along the function, that the rest of the function is always below that line. So, graphically, what this means is that the function, lies completely below the line connecting any pair of points. Right? So if I think about the functions I drew earlier, right? So this function is convex, right? Why is it convex? Because if I choose any 2 points, like say this guy, and I draw the line between them, this guy here is basically a fraction of the way from one point to the other, right? So if I call this W1 and W2, when alpha equals 1, I'm standing on W1. When alpha equals 0, I'm standing on W2. And otherwise, I'm moving in between. And this is like saying that the value of the function here is always above, the value of the function at the kind of other points, right? So here, the function is entirely below my red line. And that's true no matter what pair of points I decide to draw, right? Now, the function I drew over here is not convex, right? So if I kind of draw my squirrely function like this again, right? So it may be true locally, right? So here, yes, it's true for those 2 points, but it's definitely not true for like these 2 points, right? So if I draw this function, I can see that this is, a point on the curve that lies above the connecting line, right? So kind of what we can conclude from this is that a convex function has a unique global minimum, and that's why we like to have convex functions, right? And so let's write that down for a second. So, convex functions have global minimizers, okay? Okay, so in general, what we like to do when we pose kind of like a cost function, one good thing we like to do is to check and see, is this convex in the modeled parameters, right? If it is, then life is great. If it's not, then we can still work with it, but it's not going to be perfect, okay? And so how would we go about finding the minimum? And hopefully you remember this from calculus, right? So I don't think you probably did any sort of like numerical optimization in calculus, but you certainly talked about the gradient, right? So from calculus, you should remember that the gradient is a vector. So recall that the gradient, which we have this notation for, is a vector pointing in the direction of greatest increase. And so conversely, if I look at, minus the gradient is the direction of greatest, or maybe a better way to say is fastest decrease. In general, let's just say that any vector v, so that if I look at a given point, if I step in a little bit of a direction of v, and that's less than where I was for some alpha, is called the descent direction. Right, so it's kind of like saying I'm standing on my function, I look around, and I'm looking for a place that I can step so that the function is going to get lower, right? And the best location that I should go, the best vector I should choose, is the one where the function drops as fast as possible, and that's the negative of the gradient, okay? So kind of the name of the game is that I'm going to be taking steps down the gradient, and when do I stop? I stop when the gradient is 0, right? Because we know from calculus that the kind of definition of being a minimizer is that the gradient is flat or 0. I'm sorry, the gradient is 0 at the bottom of one of these valleys, right? So let me write that down. At the minimizer, or at a minimizer, what I have is that the gradient at that point equals 0. Right? So again, this is very much like what you learned in 1 and 2 vector calculus. Take the derivative, set it equal to 0, right? That place is where you find the minimum. Now, we definitely know that, if I have some sort of weirdo function, just having the derivative equal to 0 or the gradient equals 0 is not a necessary condition to have a minimizer. Well, okay, I'm sorry, it's not a sufficient condition to have a minimizer, right? Because there are other places where I could have 0 gradient, like at the top of the function, if there's a maximum. If there's a saddle point or an inflection point, right? You get 0 gradients there too. So it's not necessarily, the conclusive thing that a 0 gradient is the minimizer, but it is true when the function is convex, and so that's what I'm going to say in just a second. So let me give you the gradient descent algorithm, now that we kind of have this terminology here. Very easy to do. So, the gradient descent algorithm is basically the following. So we start from an initial point, let's call it W0, and then at each step that we take, we choose a step size. Let's call it alpha t. And then we take my next estimate as where I was, taking a step along the negative value of the gradient at that point. Right? So it's like saying, alpha sub t is how much of a step I take, right? Could be a small step, could be a big step, and the gradient is the direction that I'm going, okay? And so that's the simple idea. And then I basically, stop when Wt stops changing significantly. Right? So for example, what I could do is I could say I want to have the relative difference between adjacent W samples be less than some tolerance, right? So I may keep on stepping and stepping, and then eventually I stop, right? Okay. So let me pause and ask. Questions or comments about this idea? Yeah.
Back to the previous question on that. When you had the W plus and then what was it multiplied by
Alpha V, yeah.
Alpha V. Was the plus, what was the plus alpha V representing exactly?
That's like saying that, if I have W and I take a step in the direction V and the length of that step is alpha, I'm at some new point, W plus alpha V, right? And I'm saying that if there is a size of step that I can take that reduces the cost function in that direction V, then it's called a descent direction. Okay? Other questions? Okay, so, and of course, will this thing stop? Well, in addition to stopping when things start changing, what would make this cost function kind of slow down? Well, it slows down when I'm not changing W, which means that the gradient is small, right? So if the gradient is 0, if I hit a point where the gradient is actually 0, then nothing will move and I'll be done, right? So I know that this gradient descent process will stop when I hit a local minimum, okay? So that's good. And so you know, if so if my f is a differentiable convex function, then the condition for being a global minimizer is the same thing as saying that the gradient is 0 at that point. There's only one place where that works, and it's at the minimizer, okay? Which is good because, you know, let me just say that, you know, gradient descent will converge to this point, which is great. We'll talk for a second about how this convergence looks. There is definitely a black art to making gradient descent work, right? So, and it has to do with the step size. And so I'll talk about that in a little bit more detail in a few minutes, okay? So generally, this nice breeze is causing my paper to float, right? So this is why in machine learning, if at all possible, we try to use cost functions that are convex, because we know there is a global minimizer out there. We know we should be able to reach it with gradient descent. So in machine learning, we, you know, try hard to use cost functions that are convex, okay? So luckily, you know, convex functions satisfy many of the nice properties you'd like. Like if you add two convex functions together, you get a convex function, you know, but yeah, so luckily there are some nice properties of that. Like, you know, we kind of know that this quadratic function, this square function is convex. So that's nice. And as we go forward in machine learning, we'll talk more about different cost functions and kind of talk about whether they're convex or not, okay? Now, if the function isn't convex, we can still apply gradient descent, but there's no guarantee that we will converge to a global minimum. We may end up hitting a local minimum, right? So if the cost function isn't convex, we can still apply gradient descent and hope to converge to a local minimum. So what do I mean by convergence, right? So convergence basically means how fast do I get from where I started to the final answer, right? And that really critically has to do with the step size that I choose, okay? So let me just say that the rate of convergence of gradient descent is a critical thing in practice. And it depends on both the function and the step size. So, I could have a function that has got a global minimum, right? Like imagine, what's a good kind of thinking here? Imagine I'm in some sort of like canyon in Arizona, right? That's like deep and swirly. And I'm trying to find the bottom of the Grand Canyon, right? So like to get to that bottom, I may have to travel through some really narrow, twisty passages as opposed to like sloping down into some Tupperware bowl, right? So how complicated the function is has a real impact on how hard it is to reach the optimum, okay? So we kind of prefer smoother, like bowly type functions as opposed to twisty, weird functions, okay? So kind of what you do when so let me just kind of illustrate this, right? So it's like saying, suppose that I have a 1D function, right? X, f of x, right? So here in 1D, there's really only kind of like one choice. Do I move to the left or do I move to the right? So in my gradient here, I would say, well, this direction is not a descent direction because the function keeps on going up if I look that way. This is the only place I can move. And so the question is, how far should I move, right? So if I move a little bit, then my next point is here. If I move a little bit, my next point is here, right? So that's all good. If I move a little bit, maybe I hit the center, right? So in some sense, this is kind of like the just right case, right? On the other hand, suppose that my step size was tuned really small, right? So it's like, well, okay, I'm going to move just a tiny millimeter over here. Well, I am reducing the cost function, but it's going to take me forever to get to the minimum, right? I'm taking like baby steps, right? Or conversely, suppose that I take huge giant steps, right? So suppose I take like, okay, well, I know I have to go to the right at this point. I'm going to step like all the way over here, right? And now I hit this point. Or maybe I don't go all the way. Maybe I go over here and I hit this point. So it's like, oh, okay, well, I overshot. Now I have to go back this way, and I hit this point. Now I'm going to go back this way, and I hit this point, right? So if I don't choose the step size small enough, then I could end up like taking massive steps, don't worry about that, and coming back and forth, right? So it may take me a long number of steps, but because I'm kind of oscillating between two sides of the minimum, right? A different way of looking at this is kind of thinking about this from overhead, right? So if I kind of think about, a contour plot of x and y, like I could have something, if you took probability with me, right, we talked about kind of like these iso contours of probability. So if I kind of think about a topological map of the function, so a bowl-shaped function kind of looks like this. Let's suppose that I have a beautiful bowl, right? So here, if I evaluate the gradient at a point, the gradient points in the direction of greatest increase, right? So the negative gradient points in the direction of greatest decrease, right? So I would start here and I'd take a step, and then wherever I land, I'd take another step. You can see this stepping process, as long as I choose my step size correctly, is going to take me right into the center of the bowl, right? Hopefully in not too many steps. Whereas if I have a, kind of like a complicated function where in one direction the function is decreasing rapidly and the other direction it's not. So I could have a situation here where it's like, okay, here I am at this point. I take a step in the negative gradient direction. I hit this point. Okay, now I'm here. Now I could take this step here. So convergence for this function may be kind of like zigzagging back and forth, right? So the best case is you're kind of like in this world where you just take a clean number of steps and you get to the minimum. This is a situation where you may find that it takes longer to get there, right? So unlike solving a linear system where you just do, a/b and get the answer, the amount of time it may take you to minimize the function is variable, right? You can't count on getting the answer in a specific amount of time. It depends on how many steps your system is taking, which is also why typically you need to put some sort of maximum number of iterations on your gradient descent algorithm. That's always part of it. Yeah.
Is there any way to kind of like avoid that zigzag situation in that more slanted curve?
So is there any way to avoid this, right? Well, again, it has to do with how I tune the step size, right? Another way to think about this is that if I took small steps, right, then maybe if I took smaller steps, I could kind of like zone in on the answer kind of like directly, right? So instead of taking these, what's the right word, hysteresis, kind of like back and forth and back and forth. If I took small steps, then I would get down to that bowl, because the way I drew this is a convex function, right? Meaning that, I will get down there if I choose my step size accordingly, right? And so that's the thing, that's the magic, is like, okay, well, what should my alpha be at every point to make sure that I get there as fast as possible, okay? Now, as a user, you are stuck with the function, right? Like you can't really change what the function looks like, right? You can't change the shape of these contours. All you can do is hopefully choose a good starting point and then choose, a good step size regimen to get there, right? The other thing that's important is the starting point, right? So with convex functions, you will get there no matter where you start, right? But with non-convex functions, where you land generally depends on what initial point that you choose, right? So it's generally a good idea to try to get your starting point to be kind of in the, what I would call the basin of attraction of the minimum that you care about finding, right? So if I start like way far away, then I maybe find a local minimum that is like way far from the global minimum I want to find. So kind of choosing the initial point is also important to the extent that you might want to choose a whole bunch of like random initial points and see what you come up with as the best one, right? So basically you can kind of see here that just to write down what I said. So step size too big, you could bounce around. Step size too small, you could take forever. And unfortunately, there's no like mathematical magic bullet that you set up your cost function and you know what the step size should be, right? You have to try out some things. And so as we're going to talk about, especially in the context of like training a neural network, right, which is basically doing gradient descent on a certain cost function, there are kind of whole recipes for choosing the right step size at every point in time and how do you make it smaller and smaller. So kind of what you can imagine what you want to do is maybe in the beginning you take large steps, right? And then as you get a sense of the cost function, you start to reduce your step size. So when you get close to the minimum, you don't want to be taking big steps anymore. You want to be taking smaller steps. So definitely this alpha t is going to get turned down as we kind of go forward in the process. So the question of like what is the schedule for turning alpha t down is the secret sauce, okay? And so, in fact, since I'm just talking about this, why don't I just say this now? So step size kind of scheduling is important for convergence. For example, what I could do is to say, run with a constant alpha for t iterations, and then I replace alpha with, alpha times gamma, where this number is less than 1, right? So it's like I could just say, okay, after every t iterations, I'm going to reduce my step size by a certain fraction, right? Or I could say, after every, t iterations, like, so maybe something like, maybe the other way to say is like do t steps at step size alpha, 2t steps at step size alpha over 2, 4t steps at step size alpha over 4, and so on, right? So what these have in common is the alpha is getting smaller and smaller every time, okay? And again, so I thought about asking you to write a gradient descent algorithm for your homework, which is possible to do, but I also don't want you to get caught in like screwing around with step size, because these days, if we're being honest, if you use a modern optimizer in like, PyTorch or something like that, there will be built-in optimizers that are fundamentally like gradient descent algorithms that will have kind of like these pre-built kind of heuristically good schedules for tuning the step size. You shouldn't, as a user, really have to get your hands dirty with figuring out how it's changing, other than to know that that's what's happening, okay? And also to know that if your algorithm doesn't converge, well, one thing to look at is maybe I should make the step size smaller, right? That's kind of a good rule of thumb for when you're having problems, okay? Okay. So, questions? Yeah. Yep.
So the notation there are using for t iterations and then.
So it's like saying, I run with a constant step size alpha for t iterations, and then after that, I reduce alpha by a factor of gamma, right? So it's like saying maybe this gamma is like, 0.5, right, or 0.2.
Oh, actually, this is less than, it's a gamma.
Yes, less than 1. Yeah, sorry. This is some number less than 1. Yeah. Okay, so kind of more germane to, so this is what I'm telling you. What I'm telling you right now is basically like generic optimization. This function could come from anywhere, right? Any function that I want, right? And often when you see gradient descent illustrated in, textbook or Wikipedia or web app video, you'll see kind of like generic functions being minimized, right? What we care about machine learning a lot is trying to fit to data, where we have like 100 data points and we want to fit the parameters that minimize the sum of squares. And that's kind of a special setup. And then we can apply some special machine learning optimization tools to that unique case, right? So in machine learning, we often have cost functions of the form something like this. We have the sum of squares like this, right? So basically over I samples, I'm trying to minimize the difference between my model and my observation, right? The key thing here is that my cost function is made up of basically the same cost function applied to point I, okay? Sum of errors per training sample. So in this case, one thing that has proven to be very successful in practice is to not take the full gradient every time, right? So for example, in the real world, I'm training some sort of like crazy, large language model over, a data set that has 1 million examples or more, right? So in theory, to properly evaluate the gradient, I need to evaluate the direction over the sum of those 1 million samples, right? Every time I take a step. And that can be pretty, hard to compute, right? So instead, the idea is don't compute the full gradient. Compute the gradient only at a few points and take a step there and then see what happens, right? So that's an algorithm that's called stochastic gradient descent. And honestly, stochastic gradient descent is really what everyone is using in machine learning, right? So the idea is that instead of computing the kind of full or true gradient over all the points, what I do instead is I update W each time just based on, a smaller sample. Right? Maybe 1 point at a time, or 10 points at a time, or 50 points at a time, right? Then in that case, the gradient every time is much easier to evaluate, and I can take faster steps, right? And so this kind of idea is called stochastic gradient descent. Okay, so let's talk about what that means. So stochastic gradient descent. The algorithm is almost the same as regular gradient descent. Okay, so I'm going to write down the steps, right? So again, we start from an initial point W0 at each step from t equals 1 to dot, dot, dot. We again, choose a step size alpha t and a random index n in the range of the number of data points I have. So n is the number of data points in my kind of overall sum. And then what I do is I set my next guess for W to be taking a step along just the gradient of function n at W. So this is like saying I take the gradient only of this nth subfunction, not the full gradient. So, this is not as, what's the right word? Not as provable that life is going to be good as with regular gradient descent. So regular gradient descent, you have guarantees, right? But it's definitely not true that if the gradient at one of these subfunctions is 0, that the gradient of the whole function is 0, right? So there's no guarantee that if I hit 0 here, that I've minimized the entire function, right? So convergence and studying convergence with stochastic gradient descent is a lot trickier, right? It certainly works in practice, right? But it's harder to make some easy mathematical proofs of in an intro class, right? So let me just say that, and then we keep on doing this until we converge. But let me just say that convergence is less kind of straightforward or assured, because I'm not actually taking gradient descent steps along the true gradient. I'm taking an approximate gradient. I'm saying that this point that I chose is standing in for all the points, right? And so this, like I said, you see SGD, that's what it means. It's known by a bunch of other names too, right? There's something called, it's sometimes called sequential gradient descent or adaptive learning, or in signal processing it's called the LMS algorithm. They're all fundamentally the same idea of just choosing one point and taking the step, right? And so in practice, what I want to do is, shuffle through all the, so this is basically a stochastic gradient descent with exactly one sample, right? And so in practice, what I would do is I would kind of make a random permutation of all the samples, and I would step through them all. So I'm not like overemphasizing any one sample until I've gone through them all, and then I do it again. So that whole kind of outer process is called an epoch. So basically, traversing one full kind of permutation of the data points is called an epoch. So what I may do in the beginning is I may kind of like, at the first epoch, I may choose a random permutation, of the numbers 1 through 100. Then I step through those numbers, I take all my gradient steps, and then on my next epoch, I choose another random permutation and keep on doing it, right? So if you look at a machine learning, piece of code that's optimizing, you will definitely see like the number of epochs that have gone by. And machine learning optimization algorithms kind of count by epochs, right? And the epoch depends on, whether I'm doing full gradient or whether I'm doing just one sample. And of course, there is a middle step. There's a middle kind of like terrain, which is that, very common to do is what's called mini batching. So instead of just using a single candidate for the gradient, a single point, which could be very noisy, right? Instead what I do is I just choose a random set of k points and I compute their gradients and average over those k gradients, right? So instead of just using, one point in this stochastic gradient descent algorithm, instead I choose a collection of k samples. And then my update is basically saying I take the step size in the direction of the average of these k gradients. Right, so it's like saying that this number here is standing in for, again, not the full gradient, but instead of taking 1 point, maybe I take 10 points or 100 points. Depends on how big my data set is. And so this is good because, you know, the gradient at a single point is not a very good approximation of the full gradient, right? But if I average 10 points together or 12 points together or 50 points together, maybe that will be a better estimate of the gradient step. All I really need for this to do something is that the vector I choose is a descent direction, right? I don't necessarily have to be moving in the absolute best direction as long as I'm moving in a direction that reduces the cost function, right? And so by taking the average of a bunch of points, I'm more likely to be finding a good descent direction for the whole function. So this basically, you know, reduces the variance in the gradient estimate and, you know, generally better descent direction. So what happens in practice is that you, as the user, when you're setting up your machine learning optimization, will be asked to choose, like, what batch size do you want? You know, how many epochs? What optimizer do you want to use, right? And there are a whole bunch of like default choices, and you may have to kind of manipulate these choices to see what works the best for your algorithm, right? So it's definitely very common, especially as you're training like a big neural network, that, you know, the first choice that you made, well, maybe it didn't converge, or maybe you're not happy with the results, and so you run it again with a different batch size. And so again, that kind of is corresponding to this kind of outer loop of optimizing over what you'd call like hyperparameters of the problem to kind of get the best results that you can. Okay, so there's definitely no right answer that will work every time. You definitely have to play with the function to make it work. Another thing that you'll see in optimization code is what's called, you know, there's something called momentum, right? So momentum is basically saying that instead of taking the gradient at my given point and using that, instead I kind of am taking, you know, the gradient where I am right now and some sort of weighted combination of the previous gradients I chose, right? And in that way, I am hopefully going to be a little bit less swingy, right? So what we do is we mix the current gradient with the previous steps. Right? So it's like saying that I take where I am, I take a step in the gradient. So this is basically like the kind of SGD step that I would normally take. And then I also kind of like add to that the, you know, moving average of previous steps. In a way, this is kind of like saying that there's some sort of like inertia. I guess it's called momentum. So there's some sort of momentum in the system. It says if I'm already moving in this direction, you're going to keep on moving in that direction, but kind of rerouting depending on what's happening at my local point, right? So instead of like the gradient, you know, going all over the place, I have a serious bias to say, okay, you took a step in this direction, well, you're going to go kind of this step and then maybe veer off a little bit, but there's some sort of like, you know, averaging of what I did previously, right? So in practice, this also works a lot better than just doing straight stochastic gradient descent. So, you know, this has been found to work better than SGD alone. So, for example, if you were to look at the default optimizers in machine learning code, one of them is called the, atom optimizer, which is not exactly this, but the M stands for momentum, right? So it's one of the tricks that people use to do better optimization, okay? And like I said, you could take an entire course on optimization and learn lots more than what I just told you today, right? So, for an intro to machine learning course where there's lots of other topics I want to get to, I don't want to talk a lot more about optimization. We will talk about a couple other methods as we go, but this is like the key one, right? And so let me just say, what else could you learn about optimization? So let's just say there's lots more to say about optimization, right? So for example, perhaps you remember when you were trying to find a minimum in calculus that you could take the derivative and set it equal to 0, right? That's like a first order method. Or you could take the second derivative and do what's called the zero crossing, right? So there are first derivative methods and there are second derivative methods. So one thing that you could do are what are called, second order methods. Using not just the gradient, but kind of like second derivatives. And those second derivatives are called things like the Hessian and the Jacobian. I won't say too much about that. You may have seen the Jacobian when you were talking about calculus, like a change of variables involves a Jacobian. So basically, there's more to say about that. And I think that when we talk about logistic regression, I may talk a little bit about using second order methods. There's also like constrained optimization. Right? So constrained optimization is like saying, I want to minimize this function such that, some other stuff is true, right? So what we talked about so far is what I would call unconstrained minimization, meaning just find me the best W, right? Constrained minimization is like saying, find me the best W, but there's also a whole bunch of other constraints that I have to put on what W is. Maybe I want W to lie on a certain line or be in a certain region, right? So if you ever did a Lagrange multiplier problem in calculus, that's a constrained optimization problem, right? It's like saying, find me the biggest volume sphere, or the biggest volume ellipse that can fit inside this box, right? That's a standard constrained optimization algorithm, right? And then there's tons of stuff to talk about learning rate tuning. Right? That is a whole separate thing. There's something called, warm starts, which basically means, suppose that I already have what I think is a pretty good answer, right? And I want to start from that point as opposed to starting from some random point. How can I kind of also start up all the internals of this optimization algorithm, like pre-compute some gradients and stuff like that? So you may see warm start in a piece of code. And finally, we're assuming that all these variables are continuous, but what if they're not? Like, what if these are like binary variables instead of like continuous numbers, right? Well, then you get into this world of what's called like integer programming, or more generally linear programming, right? So, you could have a whole course on this or a whole course on that, right? So if you're a math major type person, then you can learn more about it. So, all right, let me stop and ask for questions, comments on this. Let me just do a worked example to make this like super clear, because I'm going to ask you to do something similar on the homework, right? So let's just do a example of how you'd compute this. So let's suppose I'm going to minimize a very simple function, right? So linear regression in 1D, right? That's like saying my model is W0 plus W1x. So I have two parameters, okay? W0 and W1. Now, I actually know that I can solve this problem directly with a linear least squares problem, right? But then again, even when you can solve the problem directly, there may be some reasons why you still want to solve it numerically, right? So say I had, a billion points, right? To form this billion by billion matrix, is probably not, or to build this matrix out of billions of points, maybe I could just solve it by doing a bunch of computationally simpler stochastic gradient descent steps and still get to the right answer, right? So there's still some reason to want to do this. And let's say we have 100 measurements. Xi, comma Ti. And let's suppose my cost function is the error over all these 100 points, where each of these error functions is like, how badly did I do at point xi? And again, I know what the model is, right? The model is saying I have my linear model minus what I saw. Okay? So the first question that we're going to need is like, what is the gradient of this guy, right? So the gradient of this guy is going to be a 2 vector because I have 2 parameters, W0 and W1, right? Well, how do I take the gradient of a function, right? So suppose I'm doing this with respect to W2 or W0, right? Well, this is a chain rule thing, right? So the outer part, if I take the 2 down, is going to be like this. So I have this number. And then what is the derivative with respect to W0 of the inner part is just 1. What is the derivative with this respect to W1 is just xi. Right? So this is the gradient of the function at point I. Okay? And so now suppose I want to do mini batching with like a batch size of 2. Okay? So let's do one step of stochastic gradient descent where I have batch size of 2. So say we do one step of stochastic gradient descent with mini batch size 2 and step size alpha equals 0.1. And let's suppose our initial guess is 1, 0. So now let's suppose I draw 2 random points out of the bag, right? The 2 points we draw, let's suppose that they are 1, 1.5 and minus 1, minus 0.5, okay? Like this is the x and this is the target. Okay, so what are we going to do, right? What we're going to do is we're going to say that my W, my new W, is going to be where I am now minus the step size times the average of the gradients, right? So we're going to have the average of the gradient whatever these 2 gradients are, okay? So let's think about what these gradients are. The gradient at the first point we have from before is, well, so the gradient of the first point is basically saying what is the error that I have? It's W0 plus W1 times x minus the target times the vector 1 times x, right? So that's going to be minus 0.5 minus 0.5. The gradient of the second point is going to be 1 plus 0 times the x value minus the y value is 0.5 times 1 times the xi value. So that's going to be 1 plus 0 plus 1.5. So this is going to be like 1.5 minus 1.5. I know it's off the screen. I apologize. Move it back up. Yeah. Right? So the average of these gradients is going to be basically well, the sum of these gradients is going to be 1 minus 2. So the average of them is going to be 0.5 minus 1. So that's like saying that my new W is going to be 10 minus 1/10 times 0.5 minus 1. So I'm going to be subtracting off 0.05, and I'm going to be adding 0.1, right? So that would be like doing one manual step of stochastic gradient descent, okay? So that's a good little exercise to make sure you understand how it all works, right? And I'm going to ask you to do something similar on the homework with obviously different cost function and different points, right? And if I was doing full stochastic gradient descent with a full epoch, then I would have to do that 50 more times by choosing 50 more or 49 more sets of random pairs of points out of the data set. Okay, so questions or comments about that process? Okay. All right, so let me then stop the recording and